Euler's identity, the most beautiful equation. Euler's identity is an equality written and named after the Swiss mathematician Leonhard Euler. It is a special case of the foundational equation in complex arithmetic called Euler's formula and has been described as the greatest equation ever. Euler's identity can be written as 0 equals e to the I pi plus 1. Euler's identity is often cited as an example of deep mathematical beauty. 3 of the basic arithmetic operations occur exactly once each: addition, multiplication, and exponentation. The identity also links 5 fundamental mathematical constants: the number 0, the number 1, the number pi, the number e, which occurs widely in mathematical analysis, and the number I, the imaginary unit of complex numbers.
I should explain a little bit about the number e, or Euler's number, which wasn't actually discovered by Euler himself. The number e is a famous irrational number and is one of the most important numbers in mathematics. The value of f of n equals 1 plus 1 over n to the nth power approaches e as n gets bigger and bigger. And as e is an irrational number, it's known to at least 1 trillion digits of accuracy. Another way it can be calculated is with an infinite series of additions, multiplications, and divisions. The value of e is also equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and etc. The first few terms add up to 1 divided by 1 plus 1 divided by 1 plus 1 divided by 2 plus 1 divided by 6 plus 1 divided by 24 plus 1 divided by 120. This equals approximately 2.71805. Writing e is like writing e to the first. To make it more general, you can write e to the x, and the series changes to 1 plus x over 1 factorial plus x to the second over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and etc. The trigonomic functions, sin x and cos x, can also be calculated by similar infinite series. Sin x equals x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the 7 over 7 factorial plus x to the ninth over 9 factorial, etc. And cos x equals 1 minus x to the second over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and so on. It looks like all these series are related somehow. If you were to add together the sin and cosine series, would you get e to the x? Cos x plus sin x equals 1 plus x over 1 factorial minus x to the second over 2 factorial minus x to the third over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial, etc. The problem is the signs in between the sin and cosine series keep changing while the Euler's number series don't. You have to multiply x by some number that when it's squared, it's equal to -1. The same when it's cubed, raised to the power of 6 and 7, and so on. That number is I. I is the only number that when squared gives a negative result. Raise e to the power of ix and you get e to the ix equals 1 plus ix over 1 factorial plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the fourth over 4 factorial, etc. But I to the second equals -1, and I to the third equals -I, and I to the fourth equals 1. Plug that into an equation, and you get EIX, and you get e to the ix equals 1 plus ix over 1 factorial minus x squared over 2 factorial minus ix cubed over 3 factorial plus x to the 4th over 4 factorial, etc. This looks like the sin-cosine series, except some of the terms are real and some are imaginary. The real terms are the ones used to find cos x, and the imaginary numbers are the ones used to find sin x. This means that cos x plus I sin x equals e to the ix. This is Euler's formula, mentioned earlier because Euler's identity is a special case of this equation.
The special case occurs when x is equal to pi, cosine of pi is equal to -1, and sine of pi is equal to 0. So e to the I pi equals 1. Rearrange this and you get e to the I pi plus 1 equals 0, or Euler's identity. What is so amazing is that in one simple equation it links 4 seemingly unrelated mathematical concepts: Euler's number, pi, cosine and sine, and the imaginary number, and that, in mathematical terms, is beautiful.